This is another big area, interconnects. People have been fascinated with it. But there are a lot of interesting things that are happening right now on interconnects on chip that are changing how we design interconnects. So this should be fun. Okay, last lecture, just to, can everybody see this from the back? It feels a little bit dark, but okay. Last lecture, we wrapped up asymmetric multi-core systems. We talked about how to handle private data locality, and we talked about how perhaps we can design systems that are much more power efficient as well as higher performance by specialization, customization, dynamically stitching together parts of the chip, asymmetric components. We also talked about a lot of cache research over the last few years. We first started with resource sharing and partitioning. What are the fundamental trade-offs between them? And then we talked about cache design for multi-core architectures, and we discussed several ideas. How to incorporate costs of a cache miss into caching decisions, how to do better, much more efficient caching by trying to figure out what blocks are likely to be reused, of course with simple mechanisms, how to do cache compression more efficiently at low latency, low decompression latency, and how to partition the caches to maximize performance, maximize fairness, and without requiring any hardware support. And we've discussed the trade-offs of all of these different mechanisms, so hopefully you remember all of these. If you don't, you can read the papers that were assigned. I'm assuming you've already done that, but maybe it was too nice of a weekend in terms of the weather. Okay, agenda for today. I intend to cover interconnect design for multi-core systems. I'll start with interconnect design in general, and we'll delve into some issues in multi-core systems. And I'll be biased again towards the research that we have been doing in the later parts of the course. And these are likely not going to be covered, especially since we have something going on downstairs. Okay, well, I'll just skip these, but these are actually at the beginning of every lecture note so that you can easily go to things that you would like to look into. So I added a couple of readings, actually. These are the readings for today. I'm going to cover most of these probably, well, however we can get to. Most of these are related to efficient interconnection network design for on-chip networks, and some of them are related to more higher performance interconnection network design and quality of service on-chip. How do you enable efficient quality of service on-chip networks? Obviously, there are a lot of interesting similarities and differences between on-chip and internet-like large-scale networks, and we've covered that also recently in some papers. I'm not going to cover these papers, but if you're coming more from a networking background and not hardware chip design background, we have a paper in SIGCOMM last year that talks about what are the differences between many-core interconnects as well as off-chip internet-like interconnects in terms of congestion and scalability behavior. And we cover buffering choices and congestion control choices that look at on-chip networks from a networking perspective. For example, one difference is in internet-like networks, you get this behavior that's called congestion collapse. The network really collapses when there's too many nodes that are injecting a lot of load into the network, and you make very slow progress. Whereas in on-chip networks, the behavior is much more controlled because it's a smaller network. You can control the injection to the network, so you don't need to collapse. Your latencies go up, but you still make progress in an on-chip network. So that paper actually covers a lot of those issues, which I think is interesting to look at these different fields. Well, different sub-areas within a field, maybe. Depends on what you consider a field. Okay, and these are the videos. And these are the videos for things and readings for things that we're not going to cover. Okay, let's start with the basics for interconnects. First of all, if you look at a scalable multi-core system, there needs to be some sort of interconnect connecting these different components, right? That's what an interconnect is. So it needs to be used to connect these shared caches that are distributed, caches and cores, as well as shared memory. So off-chip, even off-chip, you have an interconnect. Even a bus is an interconnect, right? It's a very simple interconnect. But where is the interconnect used? It is basically used to connect components, and there are many components that need to be connected: processors and processors, processors and memories, processors and caches, caches and caches, and I/O devices and other parts of the system. And we're going to abstract that as an interconnection network. In the most general form, you have an interconnection network that basically, where you can plug nodes into the network, and you don't care what node it is, as long as you satisfy the interface, where the interface is a router that connects the component to the network. And the component can be very different, right? So why is it important? This is important because it does affect the scalability of the system. If you do not have a scalable interconnection network, you cannot build a very large system. And it also affects the ease of scalability of the system. How easily can you add more processors into the system without running into performance issues? Because every time you add a node, you probably add some latency, and you may need more bandwidth. And if your network is not able to support that latency and bandwidth, you may not be able to design a scalable system. It also affects performance and increasingly energy efficiency because it affects how fast processors, cache, and memory can communicate, how long the latencies to memory are, how long the latencies of a coherence protocol are, and how much energy is spent on communication. Ideally, you would like to minimize communication, then this doesn't affect anything, but that's very tough to do. If you want to solve big problems, you need to divide the problems into pieces, and you somehow need to get the data, that's communication, and you somehow need to communicate the data between processes, which we talked about in the past lectures, and for that you need a good network. Some basics, I just want to cover the basics so that we can go into the research issues. There are three major things in an interconnection network: topology, routing, and buffering and control flow that determine the network. And these are very tightly related, actually. Topology is what the network looks like. Looks like I'm running out of batteries here, or my computer's spinning. We'll see what happens. May need to reboot. No. Or is it, maybe it's just PowerPoint, as you can see. I can go into other things, but not PowerPoint. But I'd like to record it also. Okay, this is better.
What's interesting is that I suppose your rest will appear this time because we see orange.
Oh, you see orange? Well, hopefully, let's see.
Yeah, we'll see. If you go to the first slide, we can understand whether Safari is orange or not.
Okay.
Yes, the first Safari is, if you go up to the first slide, as far as Safari is, yes.
It's orange. Looks better? Well, we'll see. But these are still red?
Really?
No. Yeah, that's. I don't think it's going to work. Okay. Let's get back to topology. Okay. So topology specifies the way switches are wired, what the network looks like, and affects pretty much everything. It affects routing, reliability, throughput, latency, and building ease of the network. We'll cover some of the topologies soon. Routing, we'll cover some of these also. It basically specifies how does a message get from source to destination. It could be static or adaptive, and we're going to cover some of the schemes. And buffering and flow control, basically, it affects a lot of things also. It's basically answering the question, what do we store within the network, and how do we store it? Do we store entire packets, parts of packets? And how do we throttle during oversubscription? Basically, how do we control the flow of packets in the network? That's what flow control means. And these are, again, tightly coupled, and we're going to cover a lot of issues related to this. Okay, this is also especially tightly coupled with the routing strategy. But obviously, topology affects the flow control as well. Again, these issues exist in large-scale networks also, so these are very fundamental and interesting. So it's good to know a lot of these topics, I think. How many of you have taken networks courses? Okay, maybe half of the class. Okay. Have you covered the topologies? Different network topologies? Okay, I'll try to go quickly then. So we'll cover some topologies, not all of them, but I think this is a fun thing to talk about. So if you look at the topologies, bus is the simplest topology, and point-to-point connections are the ideal and most costly topologies. And people have developed many different topologies to approximate point-to-point connections without the cost of it. So there are several metrics to evaluate interconnect topology. Cost is a big one. Latency is another one. And latency can be in hops or in nanoseconds, and they're not the same because you may have a very long hop, and that could take a very long time, especially given that our interconnect latencies are not scaling very well in VLSI today. And contention also is another metric. And there are many others that exist that you should think about. I'm not going to cover a lot of these. I'm going to evaluate many topologies based on this in the next in the next hour, I think. Energy, bandwidth, and overall system performance. And we're going to come back to energy and overall system performance later on. Okay. Today my PowerPoint requires a lot of attention. Okay, bus is a very simple topology. Basically, you have a bunch of nodes, and they're connected via this bus to each other. Another example is here. You have a bunch of caches that are connected via a bus to different memory banks. Okay. So this is the advantage of this is simple, and it's cost effective for a small number of nodes. And it's easy to implement coherence on this because everybody sees everybody else's actions, right? Every cache sees every other cache's actions. Seems like I need to keep clicking. It's cost effective for a small number of nodes, but as you increase the number of nodes, this doesn't scale very well. Because as you scale the number of nodes, as you keep adding things, you have limited bandwidth. When one node is transferring, if the other node also needs to transfer, it cannot, because there is only single bus. You can pipeline the bus, you still limit the bandwidth. So there are two reasons why it's not scalable. First, when there's high contention, many number of nodes that need to inject, you get to saturation quickly, because they all need to serialize over this bus. And the second reason for for this topology not being scalable is because of electrical loading. As you add more nodes, you load the bus electrically, so you'll have to operate at a reduced frequency. As a result, your bandwidth reduces. So people have moved away from buses, although hierarchical buses could be an interesting topology going forward, and people have been looking at that. IBM has many designs that have hierarchical buses, not even rings. So that's interesting to look at. But fundamentally, it's not a scalable topology unless you do you build some hierarchy on top of it. On the opposite extreme, you can connect every node point to point to every other node. That's what this looks like. Basically, you connect node 0 to every other node 1 to every other node, 2, 3, 4, 5, 6, 7 to every other node, and this is what the network looks like. And you can see that it's very complicated. The upside is there's lowest contention. When one node is communicating with another, it can use its own private channel. There is no contention between the communication of pairs of nodes. There's only contention within the communication of the same pair. Potentially, it could be lowest latency if you can design these wires to be nice and long enough, nice and short enough. And ideally, this is an ideal network if cost is not an issue, right? And if you can satisfy this part, right? The downside is not scalable for this reason, because cost is always an issue, right? Whenever people build systems and they say cost is not an issue, you should never believe them. Because people actually used to do that with supercomputers, for example. They used to think that cost is not an issue, but even supercomputer companies like Cray are very much cost limited. They may be less cost limited, but they're still cost limited. That's why engineering is an exciting field, right? We solve problems to minimize the cost. So this is highest cost because you have order of n connections, ports per node, and order of n square links. And also, there are a lot of issues related to the layout of this. Like, as you scale the number of nodes, how will you route this network? Yeah, as a result, it's not scalable. Crossbar is a step below this one. Instead of connecting things point to point, every node is connected to every other, except only one can be using the connection at a given time. Basically, it looks like this. This way, you enable concurrent message sends to non-conflicting destinations. So this node 7 can communicate with memory bank 6, for example, while node 6 is communicating with memory bank 5. There's no contention there. The only contention happens when two nodes are sending a message to a single destination. So there needs to be some arbitration there. And this is good for a small number of nodes, again, because it's costly, right? If you look at the cost, it's O(n)². This is low latency and high throughput. That's the advantage compared to bus. But it's expensive because of this. And it's difficult to arbitrate as n actually increases. And I'll show you some examples of this. This is used in core-to-cache bank networks in many processors that were initially designed. The processors that we've covered, IBM Power 5 and Niagara, had this kind of network. So this is one crossbar design. If you look at this, you'll see the arbitration problem, right? You can enable only one of these nodes to be connected to the destination node. So how do you arbitrate between these as n increases? Becomes a problem. So UltraSpark has a crossbar like this. It has cores on this side. It has cache banks on this side and a non-cacheable unit, which is a network as a 9th destination. So basically they have an interface between 8 cores and 8 L2 banks and the non-cacheable unit. And there's a crossbar that's connecting both. And this is what the crossbar looks like. Basically, this is a crossbar that connects all of the cores to bank 0. And if you look at this, there's some buffering. And this is the arbiter, which consists of a bunch of muxes, right? It's a 4-stage pipeline. You request, you arbitrate, and the arbiter selects. And in the next cycle, the transmission happens. So this is basically a router, if you will, that routes the messages coming from different cores to one destination. And they decided to put 2 deep queues so that they can ease the arbitration. Okay? So this becomes costly as you increase the size of the network. So this is a bufferless crossbar. If you look at this, it says buffered crossbar, but we'll build a bufferless crossbar soon. This is a bufferless crossbar, and arbitration of bufferless crossbar is actually more complicated because you don't know, you somehow need to directly connect these network interfaces and somehow need to arbitrate between them. Whereas if you have a buffered crossbar, what you can do is you can do the arbitration at the output over here. Right. Basically all of these channels, if you will, arbitrate for the output. And you can use flow control such that you can ensure that the buffers are not oversubscribed. Okay? I'm going through this very quickly because these are basic concepts. You can learn more about the design of the buffered crossbar later on. We're going to go into buffering choices very soon in a generic router, not necessarily a crossbar, but more of a generic router that does route, a generic switch, if you will. Okay, so with buffering, actually, you get simpler arbitration. We're going to cover this again. We'll see that you can actually get a simpler arbiter with a bufferless or minimally buffered router also. You can have efficient support for variable size packets this way, because now you can arbitrate. You can prioritize a variable size packet here, whereas it may be difficult to do in a bufferless way. But this requires n² buffers again. And keep this in mind because this is going to be a big cost of an on-chip network. Buffering may not be a big problem in an off-chip network, and certainly not in a software network. Although it is still a problem, but it's less of a problem. But as you add buffers, they consume a lot of area and power in an on-chip network. As well as this flow control mechanisms, they consume a lot of area and power. Okay, so people have asked this question for a long time. Can we get lower cost than a crossbar, yet still have low contention? So the idea of multi-stage networks have been developed for more than 40 years now. The idea of a multi-stage network is basically you have an indirect network. What it means is you have multiple layers of switches between communicating nodes. You have some source nodes and destination nodes, and you have a bunch of switches. The whole purpose of these switches are just to route the data. They're not nodes themselves. That's why this is called an indirect network. There's no direct communication. If you look at a crossbar, it's direct, right? There's no separate switch. If you look at this, the whole purpose of this is just switching. It's like a telephone network. You have switches that just switch, and you cannot call a switch in the telephone network, right? You have to call the destination. So the cost, if you look at this, is an omega network, and there are a bunch of these. And again, I'm not going to go into detail. This is a symmetric one. If you look at this, some of these are not symmetric. But the cost of this is O n log n. And the latency is log n, basically. N, if you look at this, there are 3 stages here. And you have 8 nodes, and n is the number of nodes. There are many variations. This is one of them. The trade-off these networks make is now, even for destinations that are not the same, you can get conflicts. So if you look at this, if this source needs to send to this destination, it needs to go through this route, right? But if some other source is sending to some other destination, you can still get a conflict because they need to go through this switch together. And that's a conflict that doesn't happen in a crossbar. And that's why you reduce the cost, but at the downside is you get more contention. Then the question is actually, how do you wire these switches? You reduce the contention by wiring these switches intelligently, and people have studied this for a long time. And if you're interested, this is a very exciting topic. I wouldn't suggest doing research on it because it's probably saturated quite a bit. But I think it's good to understand these going forward in building systems. So multi-stage networks, another topic is circuit switching versus packet switching. A multi-stage network can be circuit switched, right? Meaning that you first set up the path between the source and destination, and only that source-destination pair can use that path, and nothing else can use that path until that path is broken down or teared down. This places more restrictions on feasible concurrent transaction pairs, source and destination pairs, transmitter-receiver pairs. So what is the advantage of circuit switching? Because you set up the path, you don't really need a crossbar, right? You don't really need to dynamically arbitrate. Whenever a packet comes here, this switch is already set up to be wired directly. It's reconfigured, if you will. So there doesn't need to be a dynamic arbitration. This is more statically arbitrated early on. Statically meaning before the connection happens. Make sense? So the router is much simpler in this case. You just reconfigure. So it's more scalable than crossbar in cost. That's the multi-stage part. But it's more scalable. It's a more scalable switch also if you actually do it circuit switched. You could also do it packet switched. Now you don't set up the path early on. If you're communicating between 0 and 7, for example, you don't set up and dedicate that path early on. But you say, I'm going to allow all kinds of connections to be concurrent at any given time. For this, you need dynamically switched routers. Basically, the routers need to be able to dynamically connect any input to any output. And that complicates the router design here. The previous router design, it's simpler. And it doesn't need to be buffered also, actually. If you have circuit switching, you don't need to have buffers in your router. You can arbitrate early on. But packet switch is much more general, right? Because packet switch allows these 2 nodes to connect through this switch, whereas circuit switching allows only one of them to send at any given time. Okay. So just as an aside, circuit switching sets up the full path and uses that path through those routers beforehand. First, you establish the route and send the data. No one else can use those links while the path is established. Whereas packet switching routes each packet individually, possibly via different paths. If the link is free, any packet can use it, so it's more flexible. This leads to faster arbitration, simpler router, hopefully. The downside is handshake, right? This is more like you have to set up and bring down the links first, and that needs to happen. There needs to be arbitration beforehand, whereas there's no per packet arbitration. Here, packet switching is potentially slower because the router must dynamically switch, but there's no setup and bring down time. But this is more flexible. It doesn't underutilize the links. In circuit switching, when one node is not transferring data through a router, even though it already set up the path, if another node if another node actually can use that router or would like to use that router, it cannot, because the path is already reserved for someone else. So this is the choice of circuit and packet switching is independent of topology. It's actually a higher level protocol on how a message gets delivered to its destination, right? But it still does affect the choices of the router, how you design the router. Yes?
There was one problem with the previous slide.
So this one, right? It's potentially slower because you can have different.
You can just switch your data. There is no problem. The actual doing dynamic switching, you have to take some decision.
That's right.
Yes, but however, at the target, at the destination, you have to reorganize your data so as to obtain the complete data as desired. Okay. So data reorganization at the receiver part also takes some overhead.
That's true. That's true. Yes, because with circuit switching, you know who you are receiving from, and you don't need to reorganize your data.
Yes.
We'll cover that problem later on. You're right. I wasn't exhaustive in the list of things that are here, but you're absolutely right. Okay, so this is actually a higher level protocol, and people have proposed protocols for internet also, right? For circuit switching versus packet switching. ATM is a circuit switched network, for example. But some topologies are more amenable to circuit versus packet switching, and we may get back to this. Okay, another example, this is actually one of the earlier examples from Janak Patel in ISCA 1979. This is a beautiful paper to read, by the way. This is one of the earlier examples of multistage networks, maybe the first example. Basically, it shows a single path from source to destination. It's different from the Omega network because it doesn't support all possible permutations here. It was again proposed to replace costly crossbars as processor memory interconnect. At that time, people were trying to design how can we connect a large number of processors to a large number of memories in a scalable way. So this was for off-chip networks. And this was the solution. With on-chip networks, we'll see that the designs are a little bit different. But I'll let you study if you look at this, it's actually not symmetric. Okay, this is the Omega network, which is more symmetric. All stages are the same. Here, all stages are not the same because of the way things are connected. Omega network, this was in the NYU Ultra computer, which was one of the more interesting parallel machines of its time. Basically, you have single path from source to destination, and all stages are the same. And I've already shown you this, but one interesting thing they had employed in this computer was combining operations. So you could actually have routers perform computation also. So it was not just a switch, but you could, for example, add numbers. And one primitive they've introduced is the idea of fetch and add. So if you would like to, for example, increment, if you're doing barrier synchronization, and if all processors reach the barrier at the same time, and if you want to increment a shared data value, you don't need to, all processors don't need to fetch the data value to their nodes, but they can issue fetch and add operations. What fetch and add operation does is it says, fetch and add this location A, which is the lock that's protecting the barrier. And the idea is if all processors reach that, they will all somehow go through a router that receives these fetch and add messages. And the router can aggregate those fetch and add messages. Let's say this processor 000 and 001 both want to, or let's say 000 and 011 both want to increment a memory location A. Router had some logic in it that says, oh, 000 is sending a message, fetch and add location A, and 00010 is also sending a message, fetch and add location A. So I'm going to combine these messages and say fetch and add location A by twice. So they had this interesting logic that simplified a lot of these synchronization operations or work distribution operations in their parallel machine. And this is an interesting paper to read from that point of view. I'd recommend that. Okay, so let's take a look at the other side. So we're trying to simplify the network. But you can also go simpler from the other side. You can start with a bus and make it a little bit more complicated, right? And that brings you to a ring. These are, again, switches here. You have processors and memory. Basically, a ring looks like this. You connect everything as a ring. This is cheap, right? The cost is ON in this case. You have point-to-point connections between neighboring nodes on the ring. The downside is it's high latency, right? If you want to communicate between one node to another, it's order n. It could be one hop, but it could be n divided by 2 hops also. Actually, if you have a single ring, if you have a unidirectional ring, it could actually be n hops, right? N minus 1 hops. And this is also not easy to scale. One metric I will not discuss, but one metric that actually is used to evaluate networks has been bisection bandwidth. You cut the network at a place where you have the most bandwidth, and this is called the bisection bandwidth, and that's the bandwidth of the network. This remains constant as you keep adding nodes, which means that you're not, as you add nodes, you're not increasing the bandwidth in the network. So contention increases as a result, assuming the communication also scales as you add nodes. So this is actually used in many systems today, Intel latest products, as well as past products, or this is actually Knight's Corner right now, I think, or Xeon Phi. It used to be Larrabee. But past products use rings because they're simple. They're simple to implement. IBM Cell had a ring also. So many commercial systems use rings to connect caches, different from the crossbars that were in IBM Power 5 and Niagara. Okay, so a unidirectional ring, the advantage, one advantage of the ring is the router is very simple. If you look at the router, this is what it looks like. There's routing logic to inject into the ring, and there's logic to eject from the ring into the node. And that's all you need. It's a 2x2 router. The topology is simple, implementation is simple, and you get reasonable performance if n number of nodes and performance needs are relatively low. So if you can actually localize your communication really well, so this may be a good network, but it's not a very general purpose network perhaps. So you get O n cost as opposed to n log n and n squared that we've seen, and you get n divided by 2 average hops, and latency depends on the utilization. Right? So you can make this bidirectional ring, of course. In this case, it's just unidirectional. You can have bidirectional. You can have 2 directions. This reduces latency and improves scalability, but it's slightly more complex. So it makes sense, actually, to make things bidirectional because you can control things at the injection. You decide which direction to inject into in each node. You can also make things more hierarchical, and I think this becomes more interesting with rings especially. Now you have a ring that's localized here, and you have a bunch of rings that are localized, and you can have a ring that are just connecting those rings. Right? So now if you want to communicate within this ring, the communication is simple. It's a bidirectional ring. If you want to communicate from this ring to this other ring, now you need to send a message that hops into this ring and delivers the message here, right? So this becomes an interesting and more scalable topology, I think, as you go forward. And you can add more bridge routers if you want to scale this. So it turns out this, if there's a lot of communication across rings, you would like to scale this global middle ring. And how do you scale that global middle ring? By adding more taps as to where it can tap into the local rings. And this is the most complicated one. This is still 16 nodes, but you have a more complicated 2 global rings that are connecting the local rings. And this is a 3-level hierarchy that has 64 nodes, if you will. So this is actually an interesting topic. I'd be happy to talk about this with people. This is a direction that we've been looking at so that we don't need to have complicated routers in on-chip networks. So if you look at this as more scalable, it's lower latency, and obviously it's more complex. But the upside is routers themselves do not get significantly more complex. The topology gets complex, but the routers are still simple. It's just 2x2 routers. And if you want to learn more about it, this is a submission we have to Micro right now that talks about the design choices in an interconnect like this. Yes?
Reliability becomes a problem in ring networks. I mean, if a node, in a simple ring, if a node goes down, you basically lost connection, right, from one half of the network.
That's right. That's because you don't have a lot of path diversity, right? You have to go through one node to reach another node. So that's right. But if you design hopefully the router, the simple router, to be more reliable, maybe you can trade off that. It's harder to design a more complex router to be reliable, whereas it may be easier to design a simpler router to be more reliable.
Or you use double rings. I mean, those are things done in networks. I mean,
that's right.
You use double rings and you keep that.
That's right, exactly. You could use all of those tricks to make this more reliable.
Actually, I have heard of wheels. So have you compared your work with the wheel? Wheel, that is in wheel, you have instead of 4 nodes in the same ring, you have, I suppose, 8 nodes, and they are connected to one central node also.
Okay.
Have you compared your performance with
So we have not looked at that. Yeah, there are a bunch of topologies.
Wheel topology is proposed by a group in Carnegie University, and they say that is the best. They just claim the same thing. Yes.
So we have looked at the work, but we haven't compared directly. But I think it's a good idea to continue looking at this.
Because they have, I suppose, just one cross. They are just connecting one wheel to at the end of each. At the end of the cross, each cross, then at each point they have 8 nodes.
Okay, so we have looked at networks with 8 nodes in the ring, and it's not too bad. The scalability is still okay with 8 nodes. But I think a wheel certainly adds more scalability if you have a lot of communication, especially within a single ring. It'd be good to look at that. I agree. Did you have a question? Okay.
There are other mixed topologies, of course.
That's right.
Rings, like cube-connected cycles and things like that. You can combine rings with the cube. Which reliability will be better, of course, because of that cube connecting the rings.
That's right, yes.
All kind of composite topologies.
Yes, I agree. I agree. I think it's actually fun to think about a lot of these topologies, and there are a lot of issues related to reliability, performance. I just want to point this out as a hierarchical topology. I think the key thing going forward in many core systems is that we want to keep the routers to be simple. Maybe that's my bias, but if your routers are very complex, they're consuming a lot of power. So to any topology, as you said, that keeps the router simple and becomes more hierarchical, combines things such that you get good latency would be very interesting going forward. And reliability is another issue that is usually not fully tackled when you look at topology research, at least in combination with everything else. Okay. So I'd be interested in your opinion about this and others. There are other hierarchical topologies also. People have looked at hierarchical meshes, for example, meshes of meshes, and I guess meshes of buses, and buses of buses. But that's right, lots of hybrid topologies. You could be very creative here. Okay, so mesh, I just discussed. Mesh basically looks like this. So it's a two-dimensional network that looks like this, and each node is connected to its immediate 4 neighbors, north, south, east, west. And average latency is, it's n crossed again in terms of the links, and average latency is square root of n, order of square root of n. So people have looked at meshes a lot, especially recently for on-chip networks, because this is easy to lay out on chip. If you look at this, you just build this node and you stamp it out. It's like a ring, except it's more scalable potentially, right? Because you have regular and equal length links here. And you have path diversity, a little bit different from a single ring at least. There are many ways to get from one node to another. So if one node breaks down, or if one router breaks down, if one link breaks down, you can use that other ring. This also helps contention, of course, because you can communicate between many different nodes without utilizing the links. There aren't many common links, basically. Or there are many uncommon links between 2 different destination pairs, source-destination pairs. So this is used in, I guess, a commercial product, Hilera's 100-core chip, which has very wimpy cores, if you remember our discussion from 2 lectures ago. Very wimpy cores, and they're connected via the scalable interconnection network. Actually, you could argue that their interconnection network is more powerful than the cores themselves, because they have 5 different interconnection networks. And many different on-chip network prototypes also. Intel has prototypes this way. I think they called it the single-chip cloud computer, SCC.
That figure, what's this? So each of those are a node, and the circle is?
So the circle is the node. This is the router. And we'll cover this in a little bit more detail. Yeah, circle is the node itself, and this is the router that connects 4 north, south, east, west neighbors of the node. We'll cover this in a little bit more detail. This is just pictorial right now. So meshes, one downside of meshes, if you want to communicate from this node to this node, well, you need to go all the way this way, right? But if you had a connection like this that wraps around, now you're much more symmetric. So the problem is the edge nodes are not symmetric in a mesh. Because of this, performance becomes very sensitive to placement of the task. If you place a task over here, it has very few places to communicate. If you basically halve the bandwidth, its communication bandwidth. Whereas if you place the task here, its bandwidth is much higher, right?
However, in Torus, it is always equal that the path from one end to the other end is also a very long path compared to
Yes.
the short path between the two neighbors in the mesh. But
Mhm.
the one in the right hand side is very long.
Yes.
To go to the node on the left hand side.
We'll get back to that on the next slide.
So I
It
don't
looks
think includes repeaters.
It looks very long, but you can actually view the nodes.
Yes, yes.
You can actually make the nodes equal length, almost equal length. I'll show you. I'll show you with an example. So this is a logical view, but physically you won't lay it out this way. You'll actually view the nodes. Okay, so Torus avoids this problem by adding those paths that you just mentioned. The upside is again higher path diversity, and you get higher bisection bandwidth. Now, if you cut the mesh in the middle, you get some bandwidth, but you don't have these additional, these additional connections. Now you have these two additional or many additional connections that improve your bisection bandwidth. Downside is higher cost, and it's harder to lay out, as you mentioned, because you have unequal link lengths. Although you could lay it out this way, which actually it's still harder to lay out than a mesh because you need to go, you need to build the wires on top of each other, whereas mesh is nice and beautiful. But at least you get rid of the unequal link widths. And I'll let you think about this. This requires some thinking, I think, that to convince yourself that this is actually a torus, but it is actually a torus. This kind of routing, yes. You know that better, probably, I think. But torus can be a more scalable topology also, especially if you have more metal layers, right? The routing is not that bad. Okay, so trees are maybe a little bit more scalable, but these are becoming more specialized to the communication pattern also. If you look at this, a tree looks like this. It's a planar hierarchical topology by nature. And ignore this fatness for now, but assume that this is a tree, this is a binary tree. And these are the nodes, and they can communicate with each other somehow. If you look at this, the latency is O log n, right? You need to communicate. The latency scales with the log of the number of nodes. This is good for local traffic. If these nodes are communicating with each other, they don't need to go all the way to the other side, right? So if you can map your computation very nicely to this tree, you can get much better performance than a mesh, if you will. And this is actually, we already know how to design trees, right? A clock is a tree in a network, and that's a network too, when you design a chip. And we know that very well. People have optimized those designs. So we can perhaps optimize this design also. So the upside is it's cheap, ON, and it's easy to lay out also. And we know how to do that today. The downside is not all communication patterns fit nicely to this, and roots can actually become a bottleneck. Well, here you don't see the root, but you have two roots connecting the top of the trees. And fat trees actually avoid this problem. The idea of a fat tree is as you keep going up the tree, you keep the total bisection bandwidth constant, meaning that in a binary tree, you double the bandwidth over here. As you keep going up, you keep doubling the bandwidth. And this is a fat tree. This part becomes very fat because the bandwidth is very high over here. The assumption is that if the communication is uniform, you get this doesn't become a bottleneck anymore because the bandwidth is high. And these have been used in supercomputers. Connection Machine 5, which is another interesting paper. This is their fat tree. And they've used a fat tree as a communication substrate in their designs. They had basically these 4x2 switches, and they had an interesting randomized routing mechanism going from bottom to up. And I'll let you think about, I'll let you read this interesting technical summary. We won't go into detail. But they've actually used, this was a machine, this was a SIMD machine. They had 64,000 processing elements, I think. And they connected them this way. And they had a lot of operations, combining operations. These switches actually did combining that I described earlier. They had support for multicast, and they had support for reduction operators also. So my favorite example for trees, if you want to do a very large scale addition of elements in a network, basically you can do the sums going up, and you can sum up everything. You can do the partial sums, and you can propagate the partial sums, and you can do the next level sums, and you can do the next level sums, all the way up, such that you have the final sum over here if you keep your initial elements in the bottom of the tree. Right. That makes sense. That's a beautiful communication that fits the network, right? Okay. So you can go even more fancy hypercubes that you mentioned earlier, or cubes in general. Is an interesting topology, and I think this will be the last topology that I'll just throw at you. Basically, this is what it looks like. It's a hypercube, and I assume you're familiar with hypercubes. It's a cube, right? This is a 3D cube, and this is the 4D version, and this is the 5D version, I think. Or maybe this is the 4D version still. So latency here is O log n again. It scales with the log of the network. Radix is basically how many outputs and inputs the router has. That's, again, O log n, and the number of links is O n log n. And again, you can map your computation nicely to this, such that local communication is localized, so that you don't need to use those links. But the distances are not too bad. So people have actually designed this as well. This is, again, another beautiful paper for one of the early message passing supercomputers, the Cosmic Cube from Caltech. It was a 64-node message passing machine, and it looked like this, basically, I think. And it doesn't look that bad, but it was laid out like this. So you can actually connect things nicely, even though they may look bad over here. Okay, I'll recommend this paper also. There are a lot of things in this paper that talk about message passing computers and how you actually design parallel programs for a message passing machine like this, and why they did the network like this. So I'll let you read that. Okay, so let's look at some issues that are interesting in on-chip networks now. One issue that comes up a lot is how do you handle contention? Because ideally you would like a network that's really cheap, but also can support a lot of bandwidth and performance. Right? One issue in a router is how do you actually handle the contention when two packets are trying to use the same link at the same time, and this doesn't come out very well. But this packet is trying to come from here and go to this link. This packet is trying to come from here and go to this link. What do? There are actually three fundamental ways of handling this, I think. One is you can buffer one of them. You can drop one of them. Or you can misroute one of them. Misroute meaning send one of them to a destination it doesn't want to go to. Right? And I think these decisions have been overwhelmingly considered for the first one. Like people have looked at buffering a lot, but people haven't explored these options a lot, even though they're as old as buffering options in the past. But as we go into more energy efficient networks, as we need more energy efficient networks, we should probably be exploring some of these different design choices as we go forward. So I'll talk a little bit about the research that we've been doing in this area. So as long as you have a mechanism to retransmit, dropping is not bad, right?
So you have to just signal out that I have dropped the packet, so the person.
That's right. Yeah, this is like similar to some protocols in internet, like transmission control protocol, where you drop packets and somehow the sender figures out the packet is dropped and it resends the packet. You could have that sort of protocol here. Misrouting is also problematic, and we'll see some issues related to that. Buffering is the safest.
Yes.
but it's the most expensive also, right? Because now your router needs to deal with buffers and it needs to arbitrate between the buffers. These others may be simpler, right? And we'll take a look at that. So actually, I'll just give you the basic idea, but we'll come back to this again. So in deflection routing, this is a very old idea. This is another seminal paper by Paul Boran from Rand Corporation in 1962. He looked at a lot of issues in distributed communication networks at the time, and he introduced this idea, which he called hot potato routing. Basically, whenever you have two packets that are trying to use the same output port in a router, don't buffer the packets, but deflect one of them to a destination that it doesn't want to go to. So you can think of a packet like a hot potato. Nobody wants to hold it. It's too hot. Routers are trying to hold it, but the routers are always passing the packet to some other router. So let me just demonstrate this. You have these two, and this is red again. You have these two packets that are trying to go to a destination, and this is the destination. And obviously, the shortest path from this here to here is this way. If you're doing XY routing, XY means you go through X direction first and then Y direction next. And shortest path from here to here is this way. You don't need to go anywhere in the X direction, right? Because they're in the same X coordinate. So in the first cycle, these two packets arrive at this router. Now they both need to go to the same direction, right? So what does deflection routing do? Normally you would buffer one of them. What does deflection routing do? It says, red packet, you can take your destination, but blue packet, too bad, I don't have a buffer. And you're too hot, I'm going to pass you on to this router that's to my right. And that's what happens. This blue packet takes the longer, more scenic route, if you will. And it eventually arrives at its destination. Right? So that's the idea. And new traffic, in this case, can be injected whenever there's a free output link. So if you look at a router, if a node here, if it's trying to inject a packet, if all of its output links are busy, it cannot inject that packet. That's the idea. So we're going to re-examine this choice for on-chip interconnects soon. So actually, people have looked at this when they were building the internet. Should we build actually internet-like or distributed networks in a more bufferless fashion? And they figured out that the load is too high. Load would likely be very high in a network like this, such that buffering is necessary. So if you think of buffering, what it adds is it adds more capability to handle load into the network. Whereas if you're bufferless, if you do not have any buffers in the network, you cannot keep more packets in your network, right? You can think of your links as the buffers. Only your links are the buffers. And the pipeline latches, of course. I'm assuming that pipeline latches are still there if you're pipeline the network. They're different from buffers. The router itself has buffers to keep packets. Okay, we'll get back to this and we'll take a look at actually how this potentially simplifies things and also complicates things. And can we achieve a good place in the spectrum between bufferless and buffered router design. So if you look at the buffered router, that's what it looks like. You get inputs from different sides, north, south, east, west, and also the local port. And this is a mesh router. It's a two-dimensional mesh. And you get outputs to north, south, east, west, and the local also. And you need to have a 5x5 crossbar here. And I'm not going to cover a lot of the crossbar designs, but that in itself is a topic that people have explored a lot also. And you have these input buffers, and basically these are the buffers that are coming from the north direction. And you need to arbitrate for this crossbar. If two things need to go north, you need to figure out which ones actually go north, and you need to buffer the packets and do the arbitration. And that becomes hard to scale. If you keep adding buffers, the size of this becomes hard to scale. And we'll see some results in terms of what is the energy overhead of these buffers. Whereas if you have, basically, in bufferless routing, flits are buffered in pipeline latches and network links. So if you have a pipeline latch here, they're buffered here. But I'm not showing that. But you need to have some deflection routing logic. And we'll see how complicated it gets. There are a lot of interesting issues, actually, in the design of this. But before we go into that, let's take a look at some routing algorithms also. There are three types of routing algorithms in general. One is deterministic. This always chooses the same path for a communicating source-destination pair. If your source and destination are the same, you always go through the same path. XY routing that I described earlier is deterministic, right? You always go through X direction first and Y direction next. You could do YX routing also. Oblivious routing, you can choose different paths between the same source and destination pair, but you don't consider the network state. For example, you can randomly choose a different path. Adaptive routing, you can choose different paths again, but you can adapt to the network state. And these get more complicated as you go down. Then the question is, how do you do adaptation? Do you do local and global feedback? Do you actually use minimal adaptive routing? Because if you have many paths, many of those paths can be minimal. Minimal in the sense that they minimize the number of hops or number of seconds it takes to communicate. But you can also do non-minimal routing, right? And deflection routing is a non-minimal routing mechanism because you can take the longer route, right? So let's take a look at some of these, because I think these are also interesting. These are topics that people are researching in on-chip networks. As I said, all packets between the same source destination pair take the same path in deterministic routing. Dimension order routing, XY routing, which is actually used in many on-chip network prototypes today. And I think it was first used commercially in the Cray products, T3D. You do this. It's simple. It's deadlock-free. If you have buffers, you need to handle an issue called deadlock. We'll look at it very briefly because there are no cycles in resource allocation. Deadlock is whenever two things are waiting on each other and they keep waiting forever, right? And we'll see why this is deadlock-free. And this could actually lead to high contention. That's the downside, right? You may have very nice path diversity in a mesh, but you're not really exploiting that path diversity if you do this, right? So let's say this is your mesh, and these are your nodes. If you do XY routing, and let's say this node is communicating with this one, this node is with this one, this node with this one, and this node with this one, they all need to route through this direction, right? And they contend with each other. Whereas if you exploit path diversity, they can route through different directions. But then you should not be deterministic, perhaps. Or you become more complicated deterministic. But then if you're deterministic, you cannot adapt to some other communication pattern. That's the downside. So that's why adaptive routing is usually better for performance, because this doesn't exploit path diversity. Okay, so what is deadlock? This is an issue with, yes? Oh, 1 minute? Okay. Yeah, maybe you should change it right now. This may be a good time to take a break. What do you think? Or maybe we should just continue if people are okay with it. I'll take a break after some of the... We resume? Okay. So one issue that I told you earlier is deadlock that this deterministic routing eliminates. I'll briefly cover what it is because people have worked on this a lot actually, and it's interesting. And it appears mainly in buffered networks, and this is one downside of a buffered network. Deadlock is no forward progress because you have circular dependencies on resources. You get deadlock. And in this case, each packet waits for a buffer occupied by another packet downstream. So if you look at this, this is a router, and these are buffers, and this is the input selection circuit, if you will, and this is the packet progression. This packet needs to, this packet 3 needs to go here, but that buffer is being held by packet 4. Packet 4 needs to go here, but the buffer is being held by packet 1. And packet 1 needs to go here, but that buffer is being held by packet 2. And packet 2 needs to go here, but that buffer is being held by packet 3. And that's why we have a deadlock here. And you can run into these deadlock situations because of your routing algorithm. In this case, the routing algorithm is not XY. Some packets are actually going in the YX direction also. They're taking the Y path first and the X path next. And basically, how do you handle deadlock? Basically, you should ensure that these cycles do not happen somehow, right? This is a bad cycle. There are three fundamental ways of, I think, handling deadlock. there's a fourth one again. You can tell me what it is. First, you avoid cycles in routing. Whenever you design your routing algorithm, you ensure that you can never build the circular dependency. And XY routing, actually, I will ask you to think about it if you're interested in this. XY routing has that property. It doesn't have that circular, you cannot form a circular dependency. And how do you do this? There's a seminal paper that I'll briefly describe. You can restrict the turns each packet can take, and XY routing does that, so that you don't have the circular dependency. You can do other solutions. You can avoid deadlock by adding more buffering. Basically, you have these escape paths. Here, for example, you have only one path going from here to here. But if you have an escape channel that enables this packet to escape to some other buffer here, then you can fix this problem. But of course, you need to manage those escape paths nicely. Or, which is a harder problem perhaps, is you can detect and break deadlock. And this is a solution people have not examined as much, at least within the context of on-chip networks. People have tried to do this in the operating system level, because this is an issue when you have threads waiting on the same resource also, right? You can try to detect and break deadlock. You can preempt the buffers. Basically, here you can say, oh, I found the circular dependency. First of all, how do you find that circular dependency? And then how do you break it is the next question. What do you take out? Because maybe by taking out this flit, or when I say flit, it's part of a packet. This is the terminology of interconnection network. This flit or packet that's holding this buffer, maybe you're not really preventing the problem. Maybe something else is injecting over here, right? Okay, but these are the three fundamental ways. And this paper that appeared in NISCA in 1992 actually introduced a turn model to avoid deadlock. How do you design these routing algorithms to be deadlock-free? Basically, any routing algorithm can be analyzed in which packets can, in the way packets can turn in the network. Like, how do they change? How do they go from X through Y, or Y through X? Or do you have, what kind of turns do you have? And you can determine the cycles that such turns can form for a given routing algorithm. And you can prohibit just enough turns to break possible cycles. For example, in this case, you may design a routing algorithm that allows this kind of turns of packets. And this won't be deadlock-free. You may design another routing algorithm this is the XY routing algorithm, actually, that allows this kind of turns. Here you cannot have a cycle, right? This is the turn model. These turns are not allowed, whereas these turns are allowed. And I don't know what this is, but you can read the paper for that. This is actually a beautiful paper, too. Okay. One example of oblivious routing is Valiant's algorithm. This is from Leslie Valiant, who won the Turing Award, I think last year or 2 years ago. And I don't have the paper reference, but you can find it. You can search for Valiant's algorithm. This is an example of an oblivious algorithm. The idea is the goal is to balance the network load. And the idea is very simple. If you have a network, don't directly send have a heterogeneous routing algorithm, if you will. Basically, you randomly choose an intermediate destination node and route the packet to that intermediate destination, and then route the packet from there to the original destination. This randomizes the load, assuming that you randomly choose the intermediate destination. And within the source and intermediate destination to the destination, you can actually use XY routing, for example, to ensure that you don't have deadlock. And that's the idea. Or you could use any other routing also. And you can choose multiple intermediate destinations as well, right? The upside is it randomizes and balances network load, so this exploits path diversity really nicely, right? Because you're taking advantage of that path. The downside is non-minimal now, right? Your packet latency actually increases because you're adding this additional destination. You can optimize this. You can do this only on high load. So when do you really need to balance the network load? Maybe when you have high load on the network. Because if you have low load, it makes no sense to increase your latency, perhaps, right? And you can also restrict the intermediate node to be close. So for example, you can divide the network into quadrants like this. And you can, if you're communicating from here to here, and maybe this is not the best example, but maybe if you're communicating from here to here, you can only choose the intermediate node from here. but not from that part of the network. That way you can reduce the latency effect of this. Adaptive routing, this is the most complicated form of routing. It could be minimal adaptive. The router can use the network state to pick which productive output port to send a packet to. Productive means a packet always makes progress to its destination. Non-productive means packet gets away from its destination. And by definition, if you're minimal adaptive, you're always choosing a productive port, right? Otherwise, you're waiting. And non-minimal adaptive routing is you can misroute packets to non-productive output ports. And deflection routing is one example of this. Basically, whenever you adapt, an adaptation may be, let's say, you get a packet here trying to go over here, but you figure out this path is congested, you can actually send the packet toward this direction, right? That's non-minimal adaptive. I'm sorry? That's right. You need to ensure that that packet actually gets to its destination. Yeah. You need to, and here, whenever you have a non-minimal adaptive routing algorithm, you have the issue of live lock, I think, that will appear here, which is different from deadlock. Okay. So this is aware of local congestion if you have minimal adaptive algorithm. The downside is minimality restricts achievable link utilization because you can only send to a particular link. Not all, many of the other links are actually non-productive, right? You can only pick from the productive links. Whereas here you have more free in which links you pick from. You can achieve better network utilization, better load balance, but now you need to guarantee live lock freedom. What is live lock issue here? Basically, when you send a packet to a destination it really doesn't want to go to, which is not the productive port, then all routers may do the same thing, and this packet may circle in the network forever, right? It may be making progress, but it may not be making useful progress because it's always moving, but it's not going to its destination. So you need to guarantee this. So we'll talk about cheap ways of doing this. One very expensive way of doing this is basically impose a total order in the packets of the network, meaning that every packet is numbered in some way, and all routers obey that prioritization order and ensure that they deliver. They ensure that the oldest packet always gets delivered, and by the induction, every packet gets delivered, right? But that total order complicates the arbitration, and also how do you actually form the total order could be an issue in some networks. But we'll look at very cheap mechanisms to do this in bufferless networks, because bufferless routing is basically a non-minimal adaptive routing, right? If you do deflection routing, that's one form of non-minimal adaptive routing. Okay, so let's take a look at on-chip networks now. So this is hopefully a better picture, which basically shows that you have some processing element that is on-chip, and you have a router. And these processing elements could be cores, L2 banks, memory controllers, accelerators. It could be anything. And these routers connect these different processing elements. And this is an example of a 3x3 meshed. These are packet switched. And this two-dimensional mesh is the most commonly used topology, but actually ring topologies look similar, right? You can actually design a ring that looks like this. And the goal in an on-chip network is to primarily serve the cache and memory request, and some I/O requests as well. Traditionally, people have designed these routers, unless it's a ring, and the mesh routers, to have these input ports with buffers. And I'm not going to go into detail, but basically, you have a bunch of buffers for each input port. Input port can be from east, west, north, south. And within those buffers, you have virtual channels so that you can you don't have this head-of-line blocking. The idea of head-of-line blocking is you partition your buffers, you separate your buffers such that you put different flows to different buffers, and you can arbitrate among them in a round-robin manner, for example, in a simple way. You can have a single buffer, and you can identify the flows differently and do out-of-order scheduling of flows, but that becomes complicated. Here you can have queues, and you can arbitrate from only the head of the queues. This is very similar to actually what we've discussed earlier, right? If you remember out-of-order scheduling versus clustered microarchitectures. Remember I showed you the graph, not graph, but this was your instruction scheduling window, and you had this tag broadcast to figure out what you can schedule. Here, you can put everything into a single buffer, and for different flows, meaning for different source-destination pairs, you can schedule things such that you pick different source-destination pairs. But you can alternatively, you can partition this window into, in this case, let's say 3, and you can have 3 different FIFO queues, right? And this FIFO queue may have, I don't know, source 1 communicating with some other destination 1, and this FIFO queue can have source 1 communication with destination 3, and source 2 communication with destination 4. And these could be dynamically allocated, of course, right? That's the idea of these virtual channels. Basically, you partition the channel into 3 instead of having a single monolithic buffer. It's a simple idea.
Each one of these are having a different destination. Is it just based on destination?
No, it could be actually extended. Basically, each one of these is a FIFO queue, and it's allocated to a particular packet, if you will. And it could actually still have multiple packets allocated to it, but the idea is to simplify the arbitration, okay, and reduce the head-of-line blocking. Because if you have a FIFO that is of the same size total and contains all the packets, now you need to pick from the middle of the FIFO if you want to schedule. It's not a FIFO anymore. Right?
But that's for destination.
That's right, yes. That's for destination. So you could think of this as packet buffers, and they're dynamically allocated. Okay, so you can imagine the complexity of arbitration here, right? It's basically a crossbar arbiter. So to be able to, the control logic, which I'm abstracting away here, it basically needs to determine the route for each packet. It needs to allocate a virtual channel in the next router, assuming that it will win the arbitration. And it needs to allocate this crossbar. So for example, if for each output port, you need to figure out who wants that output port, and you need to arbitrate. So for the arbitration algorithm is for each output port, figure out what is picked to go next. Okay? And the complexity increases as you add more buffers, as you add more input ports, as well as more virtual channels. Okay, and that's the crossbar. That's complex. So let's broadly cover what are the on-chip differences between on-chip and off-chip interconnects. One question that often comes up is people have been designing these off-chip interconnects for decades. What's new here in on-chip interconnects, right? There are some trade-off differences. It's similar to, again, the differences that you covered between multi-core and symmetric multiprocessors, right? The trade-offs are very different. People have been designing multiprocessors for, again, decades. What's different in multi-core? There are significant differences: latency, bandwidth, resource sharing. And again, you could argue that all of these are true. But power is also an important issue. Power is also an important issue in multi-core. But on-chip advantages, there's low latency between cores. That's different. And you want to maintain that low latency with your interconnection network design. There are no pin constraints, which means that your wiring can be abundant, right, in on-chip. Rich wiring resources, again, because of that reason, as well as there's just a lot of wires. Wires don't consume as much power as off-chip. So on-chip, you have very high bandwidth, and you can also have a simpler coordination, right, between different routers, because you can imagine global control within pockets on chip. Whereas if you're off chip, it may be very costly because you have pin constraints, you have high latency, and you don't have a lot of wires. There are constraints also on chip which actually dictate the design to be different. Here you can enable new opportunities. Here you can, your design needs to be more carefully done. You have a two-dimensional substrate that limits implementable topologies. And you have energy and power consumption, which is a key concern, right? Which is less of a concern if you have off-chip, because you can always scale the power supply, whereas it's a lot more difficult to scale it on-chip. And complex algorithms are undesirable because of these reasons, right? And actually, even though there is a lot of wiring resources, logic area constrains the use of the wiring resources, right? Okay. So let's take a look at this in a little bit more detail. In terms of cost, off-chip, costs come from channels, pins, connectors and cables. If you look at a supercomputer, I don't know if you follow the high-performance computing community, but they have these top 500 supercomputers. And whenever you look at the pictures of those supercomputers, maybe they've switched to optical interconnects now. That makes things different. But cabling is one of the hard parts of that interconnect design. And all of those cables are, in fact, many of the bugs that are found in those supercomputers and that are fixed are because one cable, the operator, wired one cable to a place that it's not supposed to be wired. So you can take a look at the pictures of those computers at top500.org. So that's a big resource here. Cost comes from cables and reliability of wiring of the cables, perhaps, over there. Whereas on chip, cost is really storage and switches. Wires are actually plentiful. And somebody can do the wiring automatically also, right? Whereas off chip, it's harder. Well, even if off chip, even if you can do it automatically, somebody needs to connect those things. So this leads to networks with many white channels and few buffers, or it may be perhaps should lead to those networks. Channel characteristics are also different. On chip, you have short distance, which means that you have low latency. But also on chip, RC lines need repeaters every 1 or 2 millimeters. Right? But you can also put logic in repeaters. So there are advantages and disadvantages over here. And workloads are potentially different also, right? Perhaps in an on-chip interconnect, you design your workloads to be different. You have a multi-core cache traffic versus supercomputer interconnect traffic. Because the latencies are so high in supercomputer interconnects, maybe you don't do distributed caching as much. Whereas in multi-core, a lot of the traffic is actually cache and memory controller traffic. Okay, so one motivation of efficient interconnect is this on-chip interconnect consumes significant power, and that'll be I think that'll be most of the rest of my lecture today. People have demonstrated different types of power consumption. For example, in Intel single-chip cloud, it's about 10%. In Intel Terascale, it was about 28% of the chip power. An MIT row processor, which was one of the earliest on-chip network prototypes from 1990s, it had 36%. But here, this was very similar. This is a precursor to Tylera, actually. And they had very wimpy processors and fat interconnect. That's where the 36% comes from. So we'll talk about bufferless deflection routing to actually reduce power in die area. But before I go into it, let me talk about some research in interconnects, and then we'll take a break, and then we'll go forward. There are plenty of topics in interconnection networks, I think. This is a very open area, and with any open area, there are lots of people working on it too. So there's an upside and downside. I guess the barrier to entry is very low also. That's another reason a lot of people are working on it. Whereas the barrier to entry in an area where I described earlier, like accelerated critical sections, is very high. I think that's why fewer people are working on it in general. Barrier to entry meaning, I think, the infrastructure issues related to that. Okay, so energy and power efficient and proportional design is a very important part, I think. These are actually, again, biased by my own opinions and my view of the field. Reducing complexity, I think simplified router and protocol designs are critically important because of the differences between on-chip and off-chip interconnects. So maybe I should say novel research topics, because there are a lot of topics that are interesting to look at, but they have been covered in off-chip interconnection networks. And they are easily applicable to on-chip, I think. But this part has not been covered in off-chip interconnects as much. Adaptivity, ability to adapt to different access patterns, similar to what we've discussed in asymmetry. This is a topic that has not been covered as much, and I'm happy to talk about this. Quality of service and performance isolation, while this is very much covered in internet, for example, people have tried to build many quality of service mechanisms that never made it into internet because they changed the protocol, right? They changed the interface. But there's been a lot of interesting work. Well, they made it to the edge parts of the internet, right? For example, if you do video streaming, there are a lot of algorithms that are employed to provide quality of service to different clients that are actually receiving that video. But on-chip interconnect is very different because, again, the complexity. You need to provide quality of service to different applications. Let's say you have a cloud computer. You built this 1,000-core chip. and you're executing applications from many different users, and they're contending with each other, to provide performance isolation, to satisfy the service level agreement of each user, you need to provide quality of service in the interconnect. Or you need to isolate the applications, but then you're not sharing the interconnect. That quality of service needs to be very cheap. And I don't think I'll be able to get to it, but there will be slides in here that you can look at, and one of the readings that talks about how to do this very cheaply. Co-design of interconnects with other shared resources, again, on-chip enables this much better. So how do you co-design, for example, cores and memory controllers and the interconnect together? Maybe they should be aware of each other. Maybe the interconnect should be aware of what packet is more critical to the core. Again, I don't know if I'll be able to get to it, but there are ideas on figuring out the slack of a packet. And you can do that much easily on chip. What is the slack of the packet? Like, how much can you delay this packet without affecting performance significantly? If you can estimate that at the core, then you can inject a priority level into your packet such that the router is downstream, ensure that that packet is appropriately prioritized such that it's delayed just by the right amount, such that it doesn't affect performance. And you can do that much more easily in an on-chip interconnect. Ideas like this become more interesting, I think, when you're on-chip. Scalable topologies to many cores, this is always an issue, and the difference here is something like building a hypercube is very difficult on chip, I think. People have looked at off-chip networks, and hypercubes were perhaps nice and beautiful, but it's going to be very tough to do that on chip. So this is still an important research problem, and my slides cover some of the issues related to this. Fault tolerance, we've discussed this briefly. That's a very important topic also, and doing it with simple mechanisms, again, in on-chip is a difficult part.
What's NOx?
NOx, oh, I'm sorry, that's network on chips. Yeah, one thing I should caution you about people who work in interconnects is there's lots of terminology. I tried to minimize the terminology that I use here, but this somehow escaped. And I think the reason might be because I don't have enough space for interconnects. No, that's not a good excuse, because it seems like there would be a lot of space. But there's a lot of terminology in this area. A lot more than that I already threw at you. Okay, request prioritization, priority inversion, how to build scalable coherence. I think these are very interesting issues also. And if I get to it, I'll talk about some of these. Although I'm not sure, given the speed we have today, maybe we'll just end with energy efficiency. And new technologies are also interesting. They've always been interesting. Optical technology, people have been looking at it from an off-chip point of view, and that's happening in the off-chip world. But it's not clear if it will happen in the on-chip world. That's why it's an interesting research topic, I think. And three-dimensional interconnects is also interesting, especially when you have three-dimensional stacking of chips. So one example, I think, if we pick one of them here, is packet scheduling. If we have time, we'll talk about this also. Which packet do you choose for a given output port? Basically, router needs to prioritize between competing flits. Flit is another terminology that people have developed. Basically, you don't transmit packets in many interconnects, but you divide the packet into smaller chunks, flits, and you transmit those. Actually, there's a little bit more over there, but that's okay. We can keep this abstraction. Then the question is, which input port do you pick in the next router? Because basically you're picking, this is the output port, and this output port, which input port should you actually pick to transmit to output? Which virtual channel within this input port? And this virtual channel may contain different application packets, or input ports may contain different application packets. Which applications packet do you pick if there are multiple applications that are sharing this? So this becomes an interesting decision in an on-chip network. Whereas in a supercomputer interconnect, this was not an issue much because the application was single, right? Maybe you pick between different flows. There are common strategies that have been used. For example, you can round robin across virtual channels. If you have 4 input ports and 4 virtual channels each, you have 16 things, and you pick the non-empty virtual channel in a round-robin way. You can do all this packet first, or you can have an approximation of it. This may be fair in some definition of the word fair, but it's not clear. You can prioritize some virtual channels over others, This basically allows you to actually implement prioritization, some quality of service in the network. Or you can have better policies in a multi-core environment. You can use application characteristics, for example. You can divide the application into latency sensitive versus bandwidth sensitive and prioritize latency sensitive applications. And if I have time, I'll discuss some of these issues. Or you can design policies to minimize energy somehow, or minimize the slack of the system. Okay. Maybe we should stop here for a short time and take a 5-minute break.